When you're given a matter and a temperature, and when you're being asked for what's the physical state of the matter, how would you answer this type of question? So first, let's give a little background on what are the different state of the matters. So there are three common ones that we should know about. Uh, we all know solid, liquid, and gas. So the difference is really how compact the molecule is. As you're given energy to a certain system, by system we're talking about a certain thing, let's say a glass of water, an ice cube, or whatever you define as your system, you give more energy to it, we see the ice will melt and the water will boil. So that's called a phase transition, right? A state transition. And I just want to point out in the last picture over here, you see, so if this is, so gases, you cannot really see gas, right? So you can say, what's the black thing, space over here, there's gas, but the smoke right here, they're really solid. They're just tiny, tiny, very tiny, solid particles. And they're over here. So that's why maybe some of you can try experiments. It's really easy. If you have a candle, and you blow the candle, you can see there's smoke over there, right? And right now, if you take a lighter and you light the smoke, it will bring the fire back to the candle. Why? Because you're actually lighting up those solid particles in the air, and then they are bringing this fire back to the candle. So easy experiment, try it on your own. So I want to illustrate better on what's actually going on if you watch closer. So let's say you have a glass and you have the same amount of water and you started with them in a really cold temperature, so let's say negative 50 degrees C, right? And then these water molecules over here, so each blue dot represent each water molecule, they're actually really compact. The space between them are very small, and that's what we call a solid. And as I give it heat, it's heating it up, so the system, these molecules will get energy so they can start to move around, so they have more space between them, right? And then if I continue to heat them, they'll have even more space. Eventually they're able to escape from the system, right? And what if I actually seal a cap over here? Then you have the same amount of molecule in the glass for each system, but the pressure here will be super great because these smaller molecules really need space between each one of them, right? So it's really about expansion. So as we also, you might also know that um, stuff expand as you heat them up, right? Like a metal piece, if you heat them up, they'll expand. Why? Because they start to have more space in between them. So the whole metal bar compared to this one will have an expansion process. And so actually, I've been wondering for many years when I was first started learning chemistry, are there really just three states? But turns out there are actually a lot of states, more than you can imagine. So there are right now defined as 15 states, and there are different ways these are defined. The first way is they're called substates. So for example, within the liquid state, you can actually have a thing called liquid crystal, which is being used in liquid crystal display, where it's more commonly used in our TV, right? And then another group besides solid, liquid, and gas, which is completely different from them, are called plasmid, which are just freely charged particles. But you don't really need to know about this. I just find this very interesting, and I think it'll be cool to share this with you. So, um, besides questions on this chapter, I think what more important is common sense. There's just a few things that are common sense that we need to know. The first thing is water turning to ice at 0 degrees C. Water boils and turns into vapor at 100 degrees Celsius. And also in chemistry, sometimes in the question, they'll just specify, oh, you're doing this in standard S1 STP. So we don't have to talk about pressure right now. So STP means standard temperature and pressure, which is referring to standard temperature at 0 degrees C, standard temperature at 1 atmosphere, which means what we're experiencing right now is 1 atmosphere. And sometimes we'd say the experiment is being done at room temperature, which is usually referring to 25 degrees C. And we should also know that oxygen and nitrogen, these common gases, are usually at uh, our gas at either 0 degrees C or 25 degrees C, which is really common sense, but sometimes we don't really realize it. That's why we're breathing these airs and they're in their gaseous state. So right here you can see it's probably a liquid nitrogen tank. So right in there, they are being widely used in all kinds of wet labs and experimental settings. And they're super cold. They're more than 200 degrees C at in their liquid state. And not one last thing is that all metals are solid at room temperature with one exception, and that would be mercury. So the reason why we build all these huge structures with metal is because we know they won't melt at room temperature, right? If we have metal that melt, we will not be using it to build this tower, right? But mercury, on the contrary, is liquid, and we know that liquid kind of tend to expand a little bit when they're trying to they're being heated. So that's why we build our thermometers using putting mercuries over here, so that when the temperature heats, it expands and you get a reading. But right now everything is electronic, so uh, just keep these things in mind. And for the question time, so there is actually no direct. People don't just ask you, "Oh, is this a solid? Is this a liquid?" I think that's for 5 years old, so people don't ask the same question of this. But does not mean like we don't test this concept of um, phase transition, state transition. So, which we'll talk about in the next class. But just keep in mind, know the common sense, and there'll be a lot of other ways people are gonna test it. They test on entropy, they test on the amount of heat that's being absorbed when you go through a phase transition. But there's nothing we need to worry about right now. So see you in the next one.